equal volumes of gases at the same temperature and pressure contain the same number of molecules. So Avogadro's law is just expressing Gay-Lussac's law in terms of molecules. So we are going to get the volumes and express them in terms of molecules. For example, if we have a hydrogen gas reacting with oxygen gas, giving us water gas, put here 2, then here 2 to balance. Gay-Lussac told us that 2 volumes of hydrogen react with 1 volume of oxygen to produce 2 volumes of steam. But in terms of Avogadro's law, I can write this one in terms of molecules. For example, 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of steam. So when I talk about Avogadro's law, I express the reacting molecules in terms of molecules, and then Gay-Lussac's law, the equation is given in terms of volumes. Example 2, we have nitrogen gas reacting with hydrogen gas, giving us ammonia gas. Balance it, it is like that. Balance it, I put here 2, then I put here 3. 1 volume of nitrogen reacts with 3 volumes of hydrogen to produce 2 volumes of ammonia. This is in terms of Gay-Lussac's. Then in terms of Avogadro's law, I say 1 molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. So this law enables us to change from volumes to moles, and at the same time it can help us to change from moles to volumes. So we have the relationship between the vapor density and the relative molecular mass. So the relationship between these two, it can be given by relative molecular mass is equal to twice vapor density. So once you are given relative molecular mass, you can get vapor density by multiplying it by 2. At the same time, the vapor density is equal to half the relative molecular mass. This is the relationship between relative molecular mass and vapor density. Let us talk about the molar gas volume. Molar gas volume can be occupied by the volume occupied by 1 mole of a gas. So all gases under the same conditions of temperature and pressure occupy the same molar gas volume. So at STP, this is standard temperatures and pressure. Gases can occupy 22.4 liters. This is in terms of liters, or they can occupy 22.4 decimeter cubed, or they can occupy 22400 centimeters cubed in terms of centimeters cubed. That is at STP. Then at RTP, that is room temperature, gases can occupy 24 liters, or they can occupy 24 decimeters cubed, or they can occupy is 24,000 centimeter cubed. So at these temperatures, the molar gas volumes are these. At STP, we have this, then at room temperature, we have that. We have an example here. Determine the number of moles in the following gaseous volumes at STP. So at STP, remember, it's a reminder, at STP, gases can occupy 22.4 liters or 22.4 decimeters cubed, or 224,000 centimeters cubed. That is at STP, so don't forget about that. So part A, 1.2 decimeters cubed of nitrogen, then part B, 300 cubic centimeters of ammonia. Then the solution for part A, we know that 1 mole of a gas at STP occupies 22.4 decimeter cubed. So we write that statement. 1 mole of a gas occupies 22.4 decimeters cubed at STP. But remember, we have the volume, but we want to get the number of moles. So we change this statement such that the number of moles move to the right hand side, whereas the volume comes to the left hand side. So we say 22.4 decimeters cubed are occupied by 1 mole of a gas. Which gas is now nitrogen? So we say of nitrogen. So if 22.4 is occupied by that, one of the 1 decimeter cubed of nitrogen, 1 decimeter cubed is occupied by, let's multiply 1 times 1 divided by 24. 1 times 1 divided by 22.4. These are moles of nitrogen. So if 1 is occupied by that, what of the 1.2 decimeters cubed? 1.2 decimeter cubed is occupied by, let's multiply again, 1 times 1 over 22.4, then times the 1.2. 1.2, these are moles of nitrogen. So the answer here is 0.005 moles of nitrogen. That's our final answer. Then, part 2, they told us 300 cubic centimeters of ammonia. So, 300 cubic centimeters of ammonia. Remember, 1 mole of the gas occupies this. So, you want to get the number of moles that occupy 300 cubic centimeters of ammonia. So, use the same procedures. By this time around, we are going to use 224,000 centimeters cubed. So, we say 224,000 centimeters cubed of ammonia are occupied by 1 mole. So if 224,000 centimeters cubed of ammonia are occupied by 1 mole, what of the 1 cubic centimeters of ammonia? So 1 centimeter cubed of ammonia is occupied by, you cross multiply 1 times 1 times 1 divided by 224,000. These are now moles. So if 1 is occupied by that, one of the given volume, which is 300 cubic centimeters, so say 300 cubic centimeters of ammonia is occupied or are occupied by, cross multiply 1 times 1 over 224,000, then times this volume here, 300. These are moles. So if I put this into the bracket, we shall get 0.013 moles of ammonia. Example 2, we have calculate the relative molecular mass of Y given that 0.8 grams of Y occupies 560 centimeters cubed at STP. Solution. We want to find the relative molecular mass, but don't forget that the relative molecular mass is equal to 1 mole of a substance. And 1 mole of a substance occupies 22,400 centimeters cubed. So don't forget these 3 principles, that 1 mole of a substance is equal to the relative molecular mass. And the relative molecular mass occupies 22,400 centimeters cubed. So we are going to get the mass of this Y that occupies 22,400 centimeters cubed. In that case, we shall have gotten the relative molecular mass. So we write that 560 cubic centimeters of Y weigh 0.8 grams. So if 5.6 of Y weigh 0.8 grams, what of the 1 cubic centimeter of Y weighs, cross multiply 0.8 times 1 divided by 560. Now, if 1 cubic centimeter weighs this, what of this volume at STP, which is 22,400 centimeters cubed of Y will weigh, cross multiply again 0.8 times 1 times 22,400 centimeters cubed divided by 560. This one will give us grams, centimeters cubed, it will give us grams. Now, when you put this one to the bracket, we are going to get 32 grams. So therefore, we say the RMM of Y is equal to 32. We don't put grams because it is a relative molecular mass. Let us see how we can calculate the masses and volumes. Have an example here. 0.2 moles of ammonia gas measured at STP were passed over copper 2 oxide. The equation for the reaction is this: 2 moles of ammonia plus 3 moles of copper 2 oxide, giving us 3 moles of copper, 1 of nitrogen, then 3 of water. Calculate the number of moles of copper 2 oxide used, part B, mass of copper formed, then C, the volume of ammonia used at STP. They're telling us copper is 64. So, solution for part A, calculate the number of moles of copper 2 oxide used. So we want the moles of copper 2 oxide used. But in the question they are giving us the moles of nitrogen used. So I'm going to relate ammonia to copper 2 oxide. So I can say from the equation, 2 moles of ammonia react with 3 moles of copper 2 oxide. So if 2 moles of ammonia react with 3 moles of copper 2 oxide, what of the 1 mole of ammonia reacts with cross multiply 1 times 3 over 2 moles of copper 2 oxide. Then if 1 reacts with that, what of the given number of moles is 0.2. So 0.2 moles of ammonia react with cross multiply again 0.2 times 1 times 3 divided by 2. These are moles of copper 2 oxide. And the answer here is 0.3 moles of copper 2 oxide. Simple as that. Then part B, calculate the mass of copper formed. The mass of copper formed. So from the equation here, I can also as well get the mass of copper formed. I can get this one in two ways. Number one, relating ammonia and copper at the same time, or first finding the number of moles of copper, then I change the number of moles to mass. But it is easier to do it this way. But B, from the equation, 2 moles of ammonia react to produce 3 moles of copper. 3 moles of copper. So let me remove these moles because I need mass. Let me remove the moles and replace it with the mass. So I can say that 2 moles of ammonia react to produce. So 3 moles is the same as multiplying the other mm by 3, because each mole has or is equal to the other mm of copper. So it is 3 times 64. 64 is the other mm of copper. So these are grams now of copper. I'm repeating this. I'm changing moles to mass. Change moles to mass, I multiply 3 moles times the relative atomic mass, which is 64. So if 2 moles produce about 1 mole of ammonia react to produce cross multiply 1 times 3 times 64 divided by 2. These are grams of copper. What of the given number of moles, the 0.2? Because 2 gave 3. Then 1 gave that. What of the 0.2? So 0.2 moles of ammonia react to produce, cross multiply again. So you have 1 times 3 times 64 divided by 2 times 0.2. The whole of this is grams of copper. So our final answer will be 19.2 grams of copper. That is the mass of copper that was produced when ammonia reacted with copper to oxide. Actually, they're asking the volume of ammonia used at STP. So at STP, let's use liters. At STP, 1 mole of the gas occupies 22.4 liters. So I'm going to use this statement to find the volume of ammonia used. So here I say that because I need moles, I need volume. Let me put the mole to this side. So 1 mole of ammonia occupies 22.4 liters. So if 1 mole of ammonia occupies 22.4, what of the 0.2 moles given? So 4.2 moles of ammonia occupy, cross multiply 0.2 times 22.4 divided by 1. These are liters of ammonia. So the answer will be 4.48 liters of ammonia. So we have example 2. 2 moles of iron react with 3 moles of chlorine, giving us 2 moles of iron 3 chloride. Calculate the part A, volume of chlorine at STP required to react 8 grams of iron, then part B, mass of iron 3 chloride found. So solution. In part 1, we are going to relate the volume of chlorine to the mass of iron. So we need the volume of chlorine, so we are going to put chlorine on the right hand side. Therefore, we say 2 moles of iron react with 3 moles of chlorine. 3 moles of chlorine. So I'm going to change this one to moles, and I change this the other to liters because I need volume. So change this one to moles. I have 1 mole of iron is equal to 56. So 2 moles are 2 times 56. Now this one is grams. Because I was given grams of iron react with, I'm changing this one to volume. Let me change it to decimeters cubed. So it is 3 times 22.4 decimeters cubed. Why am I multiplying by 3? Because 1 mole occupies 22.4. Therefore, 3 moles will occupy 3 times 22.4 decimeter cubed. So to continue from here, I'll say 2 grams of iron react with 3 times 22.4 decimeters cubed. So if 112 grams of iron give us a react with that, what of the 1 gram? 1 gram of iron reacts with, cross multiply 1 times 3 times 22.4 divided by 112. These are decimeters cubed of chlorine. Therefore, if one reacts with that, what of the 80 grams of iron grams of iron react with. Again, we are going to cross multiply, having 8 times 1 times 3 times 22.4 divided by 112. These are decimeters cubed of chlorine. So when I put this one to the calculator, I'm going to get 4.8 decimeters cubed of chlorine. Then again, part 2. I have mass of iron 3 chloride formed. So I can relate again iron and 3 chloride. So part B, we have from the equation 2 moles of iron react to produce 2 moles of iron 3 chloride. So let me change the moles to masses, these moles to masses, because I need masses at the end of it all. They're asking for mass. Yet I also have the mass of iron that reacted. So here you have 2 times 56. These are now grams of iron react to produce. I'm changing this one also to mass. So the reactive atomic mass of iron is 56 plus the reactive atomic mass of chlorine is 35.5. Then times there are 3 of them. But the whole of this is times 2. So this is the relative formula mass of iron 3 chloride. This one here in brackets. But you multiply it by 2 because there are 2 moles. Because this is 1 mole, now times 2 because here you have 2 moles. So we have at the end of it all 112 grams of iron react to produce. Multiply this, we shall get 325 grams of iron 3 chloride. Now, if 112 produces that, therefore the 1 gram of iron react to produce, cross multiply again, 1 times that, 1 times 325 divided by 112 grams of iron 3 chloride. Now, what was the mass given? The mass given was 8 grams. Therefore, 8 grams of iron react to produce, cross multiply again, 8 times 1 times 32, 5 divided by 112. These are grams of iron 3 chloride. Therefore, the answer will be 23.01 grams of iron 3